Welcome to my video tutorial on Chapter 3 Turnpike.g. Now in this tutorial we will look at the problem of Chapter 3.34, the computation of the dynamics in the command optimum. The tutorial is split in three parts. In the first part we study the economic problem and find out why it is important to us welfare economics. In the second part we look at the Gauss computer code, Chapter 3 Turnpike.g. It is highly advisable that you have a little prior knowledge of Gauss computing, and if you have no prior knowledge, I would recommend to you that you first start with Chapter 3 OLG.1.g, which is the prior program in this chapter and computes the dynamics in the OLG model of section 3.2. In the third part, I will pose a new problem which is not given in the book, and you may pause this tutorial at this point and try to compute it yourself, program it yourself, and then we go through it together. So let's first look at the economic problem. Therefore, you should download my slides from my homepage on the teaching material for public economics, chapter 3, and go to page 50. Now, what is the problem, the economic problem that we would like to look at? It's a two-period overlapping generation models. It's a command optimum, so a benevolent dictator here maximizes utility of the 20-something generations. It's generations live two periods, each is equal to 30 years, and we use a production function in the form of a Cobb-Douglas. So our per capita production is given by k to the power alpha, with alpha equal to 0.36. Instantaneous utility is logarithmic, and utility is discounted with the factor beta equal to 0.4, which approximately corresponds to an annual discount rate of 3%. Population grows at 10% over this period, so it is approximately equal to 0.3% at an annual basis. Central planner weights each utility of the different generations equally, and we study the dynamics over a time horizon of 20 years. The initial capital stock is given by alpha over n to the power 1 over 1 minus alpha, which for our parameterization is equal to 7.40. And the dynamics for our command optimum for our problem are provided by equation 34a through 34c. Now we would like to compute the dynamics for the case that the initial and the final capital stock are given by 70% of the steady state capital intensity K, so are equal to 5.18 in period 0 and 21, and we would like to compute the capital stocks K1 through K20. We now can combine the equation 34a through 34c into a second order difference equation in KT, which is presented by equation 35. So K0 are given and K21 are given, and we want to compute K1 through K20 with the help of this equation. Now let me show you the solution for this problem. The solution is characterized by a hump-shaped dynamics of the capital stock. It starts with 5.17 and it ends with 1.57, and meanwhile it attains a maximum after 10 or 11 periods equal to almost 6.1. So it's very way off short of the steady state capital stock 7.4. Now, why is this behavior remarkable and interesting in itself? Let's compare it to the Ramsey model with a finite horizon, let's say where a household lives 21 periods and also has given an initial and final capital stock of 70% of the steady state capital stock in the Ramsey model. Now, if you contrast the behavior of these two models, you notice, or let me tell you, that the adjustment in the Ramsey model is much faster. So it increases much faster and approaches the steady state capital stock within a couple of periods, remains at this higher capital stock, and goes back to the final capital stock value within a couple periods. So this behavior has been named turnpike behavior. Why? Because it's like driving from a suburb in New York to a suburb in Philadelphia. You enter the motorway as fast as possible, stay on the motorway all the way from New York to Philadelphia, and just shortly before you arrive at your destination, you leave the motorway. So, or in other words, the turnpike. So what we notice here is that in our overlapping generations model, the speed of adjustment is much slower, much lower than in the case of the Ramsey model, and this has important implication for welfare economics. So for example, if you study public policy, a change in the tax rate, a change in the pension system, higher pensions, lower pensions, whatever, you notice that in the OLG model the adjustment is much slower, and this of course results in a different welfare ordering of economic policies than in the case of a Ramsey model. So if you think that the demographic structure is important to your economic problem, you should rather take the overlapping generation models because it implies significantly different dynamics. Now let's go to the numerical problem. We have given the initial capital stock K0 and the final capital stock K21. So we're looking in fact for 20 unknowns K1 through K20. Now let's notice the recursive nature of our problem, the structure of equation 35. We have K0. Now let's assume we would know the value K1. Then with the help of 35 we can compute K2 as the solution to the right hand side of equation 35. Given K1 and K2, we again can compute K3 with the help of the right hand side of equation 35, and so on. In the final iteration we have K19, K20, and we can compute K21 and compare it to our given exogenous value of K21, which is equal to 5.17. And if this is the solution, we know our chosen value for K1 is the right one. And if it's off, we have to adjust our guess for K1. So what we have done here is to reduce the numerical problem to find the solution to a nonlinear equation in 20 unknowns to one where we only have one unknown, K1. And this is what the computer program Chapter 3 Turnpike does. So let's turn to this program. Please load it into your editor, into your Gauss editor. And if you have Gauss 19 or a younger version of Gauss, please specify the variable plot style equal to 1 in equation in line 24. And if you have an older version, you may also choose plot style equal to 1. This adjustment is necessary because the graphic commands have changed in more recent version of Gauss. So I use plot style 1 and save it with pressing Ctrl S. Now let's scroll down the screen to our procedure K-dun of x. Now this is the procedure, our nonlinear equation in the variable K1. So what it does is it assigns the values of the capital stock K1 to K21 in the variable Kt, which is a vector of 22 variables, 22 entries, a dimension of 22, a column vector. In the first entry, we assign k0 the initial value. In the second entry for k1, we use our local variable x, and next we iterate over kt up to the value k22 with the time horizon chosen of 20 unknowns, and we compute kt22 as our final value in this recursive iteration. And next we compare this solution to the given exogenous value k21, and if they are equal, we are done. We have solved the equation, the nonlinear equation, in just one variable x, and otherwise we have to search again. So this is our nonlinear equation, which is a recursion over 20, an application 20 times of our dynamic equation 35. Now let's go back to the top and see if this computer works on your computer. So just press the run arrow in the top menu bar or Control R. First you find the plotting of this residual function over a range of values for the initial capital stock K1. And you can clearly see that for a value of approximately, well, 5.4 or something, we are close to the solution of this nonlinear equation. And if it falls below a certain value, below 5.3, Gauss cannot compute a solution. We will get to this in a second. I have introduced a wait statement into the program, so you have to press any key on your desk bar, and next the nonlinear equation is solved. So Kden gives you the accuracy of the solution. The accuracy is 10 to the power minus 6. And next we graph the solution, which is the dynamics of our capital stock, which is illustrated in the slides and in the book. This has been computed with the help of the nonlinear equation solver that has been programmed by Alfred Mausner and which I used in this book. Now let's see if the routine provided by Gauss also work, and this routine is called solve for equation solve, and in this case there's no convergence, so we do not find a solution for this case, and I will explain you briefly why this is the case, and then the program is finished. Now let's get back to the edit mode and look at this program in detail. For this reason, it makes sense to start the debugging mode. So press the red bug or whatever you may have. So for example, in your menu task you have debug. You may use debug. We use the red bug here in the version Gauss 19. And your screen should look something like this. So the command goes to, the arrow goes to line 16. It ignores the first 13 lines, which are just comment. Between two @ Gauss will not process the text that is contained between two @. It ignores them. It's just comments. So in these comments I include the name of the program. I specify what it's doing, the author, and the date when it was changed the last time. So now we're in the edit mode, and let's first execute the first line, new clear all, clear screen, library, graph, pgraph, and user. So what it does, it clears your memory, it loads the library pgraph into the memory, and there are certain commands from the graphics menu that are stored there, so you can generate nice graphics. If you do not know any of these commands, just go to the help function, And for example, if you do not know the command new, for example, just search for it and Gauss will provide you with an explanation. So going back into the debug mode, you may now move around with the arrows provided in the top menu bar. So you may go from line to line. Here we have plot style equal to 1. So this is for the case that you use a younger version of Gauss, for example Gauss 19. If you use an older version, you may specify this plot style equal to 0. So this depends on the version of Gauss that you use. Basically, Gauss has adjusted the graphics command between the most recent Gauss versions, and so in the Gauss version 19 you have, for example, have to use 1. If this doesn't work, please use plot style equal to 0. Now we go into the first part of the program where we parameterize the model. So we set alpha equal to 0.36, beta equal to 0.4, population growth rate n equal to 0.1, and compute the steady state capital stock k. Now in the second part we assign the initial and the final value of the capital stock equal to 70% of the steady state capital stock. So K0 is equal to 5.79 and K final is equal to 5.79 as well. So you can find out the values by just moving the cursor on top of the variable. Big T is the number of transition periods and we set it equal to 20. You may experiment around with different values, so later on you may set it to 100 to see how the behavior of the dynamics change. We store the 22 periods from period 0 to 22 in the vector TT, which is simply a column vector, and we store the solution KT in the column vector KT. So it's a column vector of 22 entries. In the following, we compute a good initial value. So for this reason, we compute the solution to our nonlinear equation k dun over a grid of the capital stock. The grid goes from k equal to 5.7 up to the final steady state 7.4 and has a grid size of 1000 equally spaced grid points, and we just compute the solution to this nonlinear equation at each grid point. So, and the solution is stored in Y grid. So here we have the iteration, the loop, where we compute the 1000 values. And here in the variable temp, we store the solution. Now the variable temp is a vector with two entries, the grid point of the capital stock K1, starting from 5.78 up to the steady state. Now you can see that the entries in the first rows are missing data. So our problem was our computer program was not able to compute a solution to this. Now in order to understand this, go back to our slides, see the dynamics, and let me tell you what's happening. If as an initial capital stock at period 1 you choose a value that is too low, K1, our iteration over KT implies that the capital stock at some period prior to period 21 gets negative. Now if you look at the term k to the power alpha, we ask Gauss to compute the exponential of a negative number. So let's say minus 1.2 to the power of 0.36. Now Gauss cannot compute this this command, cannot execute this command, cannot compute, for example, the square of minus 1, and breaks down and returns what is called a missing value. So let's return to our Gauss computer program. What we have to do in this case, of course, is to delete all the entries in this matrix temp that have missing values. And we do this by the command that's stated on the right hand side on line 53. So we delete all the lines in the matrix temp that fulfill the following condition, that the second entry is equal to a missing value. Now be careful to include the dot sign in front of the two equal signs. This means it's compared entry-wise, so for each individual element. And you can look up the syntax of our command delf again in the help function. So you need to include a matrix and a logical operator x and e, and you find a description here below how you can use it. So let's go back to our debugger. So what this line does, it simply erases all the line with a missing value, and we are left with the values for the capital intensity that provides a solution to our equation 35. So for example, for the first entry, K1 equal to 5.279690, K dun takes the value minus 8.317. Now we can graph our solution, which is done in the following lines. We just set all the plot behaviors, and now in this picture you find, given our initial values, what is the value of K dun. And we have just, of course, only graphed the values of the capital stock K1 that do not imply a missing value for the solution of our nonlinear equation. We call this the residual function. So let's close this window and go back to the debug. Here we have introduced the wait statement, which we should either, if you have the program input output here on your screen, just go there, or go back to the command screen where you have to just press any key and get to the line 76 where you use K1 as an initial guess for the solution of our nonlinear problem. I just use 10%, a value 10% in excess of the initial capital stock. We could have used, of course, the minimum from our former computation of TEM1. So we could have used the value that is closest to a K dun equal to 0. And next we have the solution to the nonlinear equation problem. What's the syntax? We need to provide an initial value, K1, which is in our case 5.7, so 110% of K0. We have to provide the nonlinear equation K dun, and we have get a solution K1, and grid contains contains information whether the nonlinear equation solver has been successful or not. So let's just click on and see how grid looks like. So if the first entry into this vector crit with the criterion is 0, it means that iteration was fine. We found a nonlinear equation problems, and for example in line 5 you find the number of iterations 4, and you find the accuracy and so on. Please do not forget to specify an ampersand in front of your procedure of your nonlinear equation that you would like to solve. So in line 79 I ask the code to stop, to wait, to introduce a wait statement if there's no convergence. In line 82 the program informs you about the return code, which is fine, and it also gives you the value of the nonlinear equation k dun at the solution k1, which is equal to 0, 1.42 to the times 10 to the power minus 6. So that's the accuracy of our nonlinear equation problems, and I've introduced another wait statement. If everything is fine, so if the first entry into the vector crit is 0, the solution is plotted, and we get to the dynamics that is illustrated in the slides and in my book. So everything is fine here. Now let's go back to the debug mode and continue our computation. We still have to press wait statement again and see if equation solve, the nonlinear equation solver provided by Gauss, works. So let's try equal solve again by providing the same initial value k1, using the same procedure k dun with the ampersand, and see if it computes a solution. And in this case our criterion here is -1, which means there was no convergence, we did not find a value. So we had problems with the use of the nonlinear equation solver equal solved, and in this case only the procedure programmed by Alfred Mausner has been successful. So this concludes our second part. We have now computed the solution for our numerical problem. Now let's go to the third part. As one exercise, you can try to reprogram this chapter 3 turnpike.g and try to solve it backwardly, so that you provide an initial value for k20, and with the help of k21 and k20 compute the solution k19, and from k19 and k20 you can go back to k18 and so on up to k0, and then compare the solution from this nonlinear equation with your exogenously given initial value k0, and if it's equal you have found a solution, otherwise you haven't. Now in this case you need to adjust your k dun, and in fact have to solve this second order difference equation for kti minus 2. And in order to do this, you have to solve a nonlinear equation. So what you have to do is you have to solve a nonlinear equation problems within your nonlinear equation problems. So this is a very rewarding exercise, and I would like you to ask to do it. What we will do in the following is we will consider another exercise. In this exercise we would like to reformulate our problem in a nonlinear equations problems in 20 unknowns, in the unknowns k1 through k20. So we would like to solve the nonlinear equation 35 for k1 and k20, and of course we therefore have to provide a nonlinear equation of the order of 20, and this will be our nonlinear equation 35 for t equal to 0, 1, 2, and so on up to 90. So let's go through these steps together. Therefore, get into the edit mode. And the first thing when you try to program a new application and using old material, old and older program, is to save the program with a different name. So in this case we choose, let's say, chapter 3 Turnpike multivariate.g, for example. So I have to use multivariate 2. So let me rename the program and adjust the header accordingly. And today is May 22. So let's save this file and change it according to the new problem. And in order to do so, let's go to procedure KD and start reformulating the nonlinear equation. So now we have a nonlinear equation in 20 variables, and these 20 variables are stored in the variable y. So what we would like to do is to return the variable y. It has the same dimension, it must have the same dimension as the variable x, and we also must include the variable y as a new local variable. We also use kt0, the capital stock, as a new variable, and kt0 is also our capital stock from period 0 through period 21. So it has big T plus 2 entries. The first entry is K0, which is given. The next big T entries are provided by our unknown x, which is a vector of 20 variables. And now we have to iterate over this equation here, over our equation 35 in the book. And have to introduce the following changes. So let's erase the right hand side. And see if we can improve the display so that you can read. So what we have done here eventually is that we have reordered the nonlinear equation 35. So this is equation 35. We start with I equal to 2, increase it by 1 so that we have I equal to 3 is our first entry in this loop, in this iteration. So y of 1 is equal to this nonlinear equation in kt of 1, kt of 2, and kt of 3. We also have to change kt to kt0 so that we only consider local variables here in this loop and do not make a mistake because we perhaps copy a global variable from above. So this is our nonlinear equation here for our dynamic equation 35 for the periods t equal to 1 up to 19, 0 up to 19. and we return our variable y. And sorry, I forgot, we also have to introduce the final value, which is k final. So this should be it. This is our new nonlinear equation system in 20 variables, and it consists of 20 equations y from y1 to y20. Next, go up in the program and see if we have to change something else. Let's erase part equations lines 48 through 73, where we have just plotted k dun. Now we cannot plot the function k dun variate because we have a function of dimension 20. We have to adjust the procedure that we provide for the nonlinear equation system, and we have to provide a different initial guess, because now our variable is a vector of length 20, and we have to provide a new initial value k1. So could be the new initial value? Well, let's start with the easiest, that our capital stock stays constant over the whole period. So in line 49, in the new line 49, we provide a new initial value which simply states, well, capital stock stays constant over the next 20, over the period 1 through 20. So K1, K2, K3, and so on are equal to the initial and the final value. And therefore we can be sure, of course, that our function k-dun multivariate does provide a solution and not a missing value, because all entries are positive and we do not have a problem to compute the exponential of such a number. Next, we want to find out what's the solution. So the solution k1, and we use the new vector kt. So we have to add the initial and the final value of the capital stock to the solution. Let's also erase the next couple of code, and then we can again plot kt with the help of our commands. And just let's also erase the rest of this program. So let's see if this works. Save it and press run. Well, residual function k-dun. Okay, here we compute the old program because I have not changed the program here. What I need to do is I have to run the program that's in the editor now. So let's press Ctrl R. And we see we have made a mistake here in line 95. So let's go to line 95. We have indexed a matrix as a vector. So let's see where we have mistyped here above. It should be y is equal to 0, big T, and one-dimensional column vector, so it must be 1. There's the mistake. And now let's run it again after we have corrected it, and you can see with the help of this new program, with this new exercise, we have computed the same dynamics but used a different algorithm here, we solved a nonlinear equation problems in 20 unknowns. So this concludes our computation here, and I thank you for your attention. If you have any other questions, please do not hesitate to send me an email, and I will be happy to answer it in due courses.